Okay, so we're discussing the stress-strain curve. Now, we've drawn the ideal stress-strain curve, but before we proceed further, let's discuss exactly what that idealization is about. Now, having said this at this point, I should also probably emphasize that your book has very nice plots of stress-strain curves for many different kinds of material. So I think that's the best way to see what reality is like. But let me try to explain the nature of the stress-strain curve further and also indicate why the one that I have drawn is in some sense idealized. Now, the first thing I will probably mention is the physics of the stress-strain curve. Now, I will put physics in quotes because the topic really falls not in this course, but more so in your chemistry course associated with materials science. But let me just emphasize why the stress-strain curve looks the way it does, at least for both metals. What we should realize is that the particular type of material we pick strongly influences, first of all, what the stress-strain curve ultimately looks like. So, for instance, although I have used at some point the easily deformable rubber-like specimen at some point during the last discussion, well, these deformations are mostly elastic. How do I know? Because when I unload the specimen, I load it and I unload it, it looks virtually the same. So when I pull on the specimen, and I can certainly break it, it will deform not perfectly but almost elastically, so to a large extent elastically until failure. And then it will, at some point at failure, it will just break apart, right? So deformations are almost, not exact, but almost elastic all the way to failure. Now, however, for these two types of specimens, metal and polymer, they will have significant plastic deformations, but the way those curves look will be different. I'm going to emphasize that in a second as well. So now, however, apart from the specimen effect, first of all, let's talk about, especially for metals, what the idealization is and why the stress-strain curve looks the way it does. Now, first of all, the stress-strain curve will always, if you're carefully carrying out the test, have always a portion where the relation between stress and strain is linear. So that's our nice linear elastic relation, right? Now, there are certain materials for which there is no dominant plastic portion. So in other words, you pull on the specimen and it will break at some point with no virtual deviation from, or very little deviation from, this linear curve. That would be an ideal brittle material. But even if you have a metal, it is conceivable that the metal actually could perhaps continue to behave in an elastic fashion, and at some point just break. Okay, so that would be fracture. Now, this, I'm mostly talking about a metal, by the way, and metals have a crystalline structure. So a crystal is a very well, nice ordered stack of atoms, if you like. Almost all metals have a crystalline structure. And it is actually theoretically possible that, think of these essentially, if you like, a crystal is like, if you like, a stack of atoms in 2D, and the atoms, of course, interact with each other. It doesn't have to be only with the nearest ones. This one can interact with that one as well through atomic nuclear forces. But we can think of these as beads, if you like, connected to each other with springs. Okay. in some fashion, and eventually if I am pulling in this direction, eventually the forces could be strong enough to fracture these virtual springs between the nuclei and cause the material to fail. So in this picture, this is a very ideal picture. The atoms, the nuclei extend under the application of the force. So this, if you like, is a extremely zoomed portion of a test specimen. Okay, as I pull, and at some point the loads are large enough to move the atoms sufficiently far away from their equilibrium positions such that they cannot sustain that close proximity between each other anymore, and they just move away from each other. In other words, you break the specimen apart. Okay. So by the way, just a parenthesis, it would be nice if you actually read into the suggested portions of the test book and complement this discussion with the discussions in the book as well, to give you a better picture of how this could happen. Now, in this picture, deformations are elastic all the way to failure. And you can theoretically calculate this value, and it turns out that if this happened, the fracture strength of the material, which is in this picture the same as ultimate because there is only one very large value, and it is the value at failure, this value would be very, very large. And in practice, you never observe such a large fracture value. Now, that is because the metals indeed do have a crystalline structure, but that crystalline structure is not perfect. There are so-called imperfections, and among many of these imperfections, dislocations are a big game changer. Now, it turns out that because there are so-called dislocations, or essentially disordered portions in this crystalline structure of the metal does not break by bonds which extend to a limit and then just vanish. Instead, the bonds are always there, but the metal deforms in a different fashion. And the way this happens depends on the exact crystalline structure of the metal. Now, if you were to have a metal where the crystalline structure is one and the same throughout the whole specimen, and that would be called a single crystal, then a almost perfect stress-strain curve is observed. Now, perfect with respect to what? With respect to our definition of elastic, perfectly plastic material behavior, right? This is what we have seen starting with ME 101. Okay, so the material has a elastic portion, and then there is the onset of yielding, and then the stress cannot increase further. The material just yields, and the stress remains a constant. Now, but this is also not what we observe in a stress-strain curve. Instead, what we observe is something in between. Okay? Something in between. So eventually we know that it goes like this. Perhaps there is an ultimate strength, the strain curve further goes down, etc. But in reality, this is what we observe, because most metals in application, they don't have a single crystal, but they have a polycrystalline structure. Okay, so here, single should be compared against poly. In other words, locally, in different portions, there are such perfectly ordered nuclei, but the orientation can change from point to point throughout this metallic structure, throughout the specimen. There are grains, so-called grains of different crystal orientation, and associated with those differing orientations, the dislocation motion is prohibited to a large extent, and when the material tries to deform, it cannot deform as easily as it could in a single crystal, and instead it follows a increasing stress strain curve, and that's because of this polycrystal structure. Okay, so again, this is just a note. You're going to learn the details, the detailed physics of how and why this happens in your chemistry class. But the point here is that yes, a material could ideally fail in a perfectly elastic fashion, elastic all the way to failure, then this would indicate a very, very high fracture strength, in fact much larger than the ultimate strength that we observe in reality. But that doesn't happen. What we could observe in reality with a single crystal is a perfect elastic, perfectly plastic behavior, but that also doesn't happen. What we obtain is something in between, and that's because of the real structure of metals. Okay, so now let's put that discussion also to a side. What we are now emphasizing or focusing on is this ideal stress strain curve that we observe for most metallic structures. Okay, so we are now going to discuss the extent of idealization. So how do real curves look? Okay. Now, the curve, the ideal curve that I am drawing is this one. It's always stress versus strain, goes without saying, and we have this nice linear portion, and then there's this plastic portion. Okay. Now this, it turns out, is not the reality. In reality, the elastic portion is actually very, very small. So this perhaps even is not a good enough depiction of reality, but really I should be drawing the stress strain curve like this, where the plastic portion is always very easily identifiable, but the elastic portion is so steep that you can barely distinguish it from the vertical axis. Okay, so this is closer to reality. So the first idealization that we are making for visual purposes is this very low gradient of the elastic portion. In reality, the elastic region is comparatively small in ductile materials. Okay, so in the previous topic, when we were talking about failure, we already mentioned qualitatively ductile versus brittle, but I'm about to re-mention the distinction again very soon. Now, the second point that we are going to make is about this point where we have a distinct deviation from the linear behavior between stress and strain. So, okay, well, now what we are saying is I'm going to take these idealizations one at a time. So again, because it's easy to draw, I'm going to draw the elastic portion with a very low slope. In reality, should be much steeper, right? And we're going to focus on this corner. In reality, you don't observe such a corner. In reality, when you do the stress strain, when you do the uniaxial tension test, what you get is a curve that looks like that, right? So yes, in this region, the curve is almost linear, and yes, in that region, the slope of the curve has changed appreciably, but unlike the idealized version, in reality, there really is no distinct point where the deviation from linearity to plastic region occurs. So in other words, you don't have a corner. Okay, so the yield strength or stress is rarely easily identifiable. Okay, that's the second point. Now, the third point is the distinction between ductile versus brittle. Okay, the curve that we are drawing, okay, now let's draw this one again. Right. This curve is more like a curve that's for a ductile material versus one that is for a brittle material. For a brittle material, you can have some elasticity, perhaps some plasticity as well, not necessarily zero plasticity, some plasticity, but not much. Okay, so brittle versus ductile is just a relative term, but certainly we can say in this case that the material on the right is more brittle with respect to the one on the left, or the one on the left is more ductile with respect to the one on the right. Okay, so qualitatively what you could observe is a strain of say 0.15 at failure, let's say for a ductile material, and for a brittle material this could be say 0.01, right? So quantitatively ductile versus brittle reflects in the fracture strain, or the strain at fracture for the material. So the point is, some materials are brittle, not all of them behave like our idealized stress strain curve. All right, well, now the fourth point that we can make is regarding the influence of the choice of the material for our specimen. So we might be interested in a metal. Okay, that's our idealized stress strain curve. Or we might be interested in a polymeric specimen. Usually they have a smaller Young's modulus. Yes, eventually they do yield at some point, and then they do follow a similar curve, but some of them, in particular the one that we are going to test in our lab experiment, they behave like this. Okay? So this is a metallic specimen. This one is a polymeric specimen. Okay. So what you see is that a metal has a smaller strength, but much higher ductility. In other words, the strain to fracture is much larger, stresses overall are smaller, and what's more, because of the physics of polymer failure or polymer behavior, when the stress strain curve decreases, it turns out it can afterwards start to increase once again. This is something that you don't observe for metals in general, but for polymers this is certainly a possibility, at least for some of them. Okay. So even strong polymers are highly deformable, but stresses involved are much smaller. Okay. Sometimes I might be exaggerating the extent to which polymer behavior differs from metals, as I've done here, but these certainly reflect general qualitative trends. All right. Well, there are a few other things that we can certainly emphasize, and that is associated with how the test itself is carried out. Okay, so What I'm going to do is I'm going to take, if you like, a metal specimen on the left and a polymeric specimen on the right. Now it turns out the effects that I'm going to mention are observed in both types of materials, but I'm drawing curves that are associated with either metals or polymers in each plot. So now what we are going to do is we're going to take a metallic test specimen. It's the same specimen. So there are many different types of metals, right? It could be steel, copper, bronze, whatever. And each of them have, depending on their exact constituents, so how you have alloyed it, how you've manufactured it, how you've treated it, they will have different stress strain curves. But we take a single material. It's very well defined. I know what it's been through. And then I take that specimen and do a test with it. And here you go. We observe our usual stress strain curve. Now, I do that test with in a situation where, again, I'll take this rubber specimen, but we're talking about metals. Deformation mechanisms are different, but I'm just trying to emphasize the deformation extent and speed here. So I'm doing this test by pulling on the specimen very, very slowly. So in fact, the speed that I'm pulling the specimen with is already very fast for a metal, but okay, let's assume I do it very, very slowly. Okay, then I do the same test again, but this time I pull much faster. Okay, so the first one extremely slowly, the second one much faster. Okay, and when I do the test, it turns out the elastic portion of the curve doesn't change much, but the plastic portion does. In particular, the ultimate strength increases, the fracture strain decreases. And I do it faster even. Again, the elastic portion doesn't change much, the ultimate strength increases, and in fact, that might be the end of the test as well. So in this direction, what is happening is that the rate of the strain, so this dot indicates derivative with respect to time. So the rate of change of strain with respect to time is increasing. I'm going to pull the specimen from its initial length to a gauge portion elongation of, say, 1 centimeter, and I can do it in 1 hour, or I can do it in half a second. Okay, so that's what's increasing here. And that's how the stress strain curve changes. So what we are observing here is that the strain rate certainly influences the stress strain curve. So when you see a stress strain curve both for metals and polymers, one thing you should certainly ask if you've already not been delivered this information is the circumstances, the conditions under which that test has been carried out. Yes, you know the specimen, you know the material, you know the geometry, but what are the conditions under which that test has been carried out? In particular, what is the strain rate? Because that rate will influence the stress strain curve. Now, this is the first thing we should ask. The second thing we should ask is, what is the temperature under which the test has been carried out? And this is an effect that we can easily see for polymers. Now, let's draw an idealized curve for a polymer. Let us say that this test has been carried out at 80 degrees Celsius. It's a relatively it's certainly not room temperature. It's a relatively high temperature for most polymers. So now what we do is now we decrease the temperature towards room temperature, and what you will observe is that the elastic portion of the curve, supposing that these tests are all carried out at very, very low strain rates, so I'm pulling on the specimen very slowly, still what you observe is because the temperature changes, in this case, let's say temperature decreases towards room temperature, the stress strain curve will start to look different. Okay, this is now for a lower temperature, say 60 degrees Celsius, what the stress strain curve looks like. And if you decrease it further, let's say to room temperature, and then to 0 or sub-0 degree, and then eventually to, let's say, minus 40 degrees Celsius, this is eventually what the stress strain curve looks like. So what is changing here is, okay, the temperature is actually in that direction decreasing. Okay, so a decreasing temperature causes the material to behave in a more brittle fashion, and at the same time, however, in a stronger fashion. So the characteristics of the stress strain curve change drastically. All that we are changing is the temperature. So here I have idealized the curves with having metals in my mind, and here I had polymers in my mind, but in reality, these effects are observed for both types of materials. Temperature and strain rate influence the material behavior significantly. When we eventually talk about viscoelasticity, we are going to incorporate the effect of the strain rate and of the temperature to a certain extent. We're not going to be discussing the influence of temperature and strain rate in the context of plasticity, but at least at some point you will see how these experimental variables eventually could influence the material behavior and how we could model it. So the point here is that when sigma epsilon is given, we should ask, right, what the strain rate is and what the temperature is.